Welcome to the Deep Dive. So today we're really jumping into, well, probably the most radical scientific shift ever, right? The birth of quantum theory.
Definitely up there.
And we're going to focus on the key players, Max Planck and Niels Bohr. These two basically turned everything upside down, took the, comfortable old physics and just changed reality.
They really did. And, to get how huge this was, you kind of have to picture physics back around 1900. It wasn't like everyone was expecting big changes.
No, quite the opposite.
Exactly. Total confidence. Complacency, almost. There is this famous claim by Albert Michelson, the American physicist, back in 1894. He said, look, all the grand underlying principles, they're set, done.
Wow. So physics was basically all finished. The only thing left was polishing the details.
Pretty much. Michelson actually said future work would be mostly about rigorous application and finding tiny effects in the sixth place of decimals.
Incredible. And then, bam, within like 10 years, you get Einstein changing space and time.
Yeah, relativity. And at the same time, Planck and Bohr completely rewriting the rules for energy and matter. Turns out the old rules were, well, just approximations for the big stuff.
So our mission today is to get into those core ideas from Planck and Bohr, the really counterintuitive stuff, how they tackled these problems classical physics couldn't touch.
Right, and how that groundwork, bizarre as it seemed, underpins almost all our modern tech.
Okay, let's dive in. We should start with Max Planck, right? This so-called reluctant revolutionary.
Yeah, Planck's a great starting point because his motivation wasn't some, abstract search for truth initially. It was super practical.
He was helping industry.
Exactly. Around 1894 in Berlin, electrical companies basically hired him. They wanted more efficient light bulbs. Simple as that.
Huh. So he's studying how hot things glow, black body radiation.
That's the one, how energy is emitted across different wavelengths of light. It was a known problem in thermodynamics, but also key for lighting.
And this practical problem slammed him right into a massive theoretical wall, the ultraviolet catastrophe. Sounds dramatic.
It was dramatic, for physics anyway. See, physicists use this ideal concept, a black body, something that absorbs and emits all radiation perfectly.
Okay, like a theoretical ideal oven.
Sort of. And the existing laws, electromagnetism, specifically work by Rayleigh and Jeans, they predicted what should happen when you heat it up.
And what was that?
That as the wavelength of light got shorter, moving towards blue, violet, ultraviolet, the energy emitted should just skyrocket, go up and up exponentially towards infinity.
Wait, infinite energy coming out of a hot object? That can't be right.
Precisely. Experiments showed the exact opposite. You get a peak, and then as you go into the UV, the energy output drops off sharply. But the math, the trusted laws, predicted infinite ultraviolet energy, a catastrophe for the theory.
So the fundamental laws were wrong. And this wasn't a new problem.
No, it had been nagging physicists for like 50 years, a constant thorn in the side. Everyone knew something was deeply wrong, but nobody could fix it without breaking the laws of physics.
Which brings us back to Planck. He was famously conservative, wasn't he? Believed deeply in those classical laws.
Absolutely. He revered classical physics. That's why what he did next was, in his own words, an act of desperation. He started playing with statistics.
Statistics, like probability, moving away from certainty?
Yeah, influenced by Ludwig Boltzmann's work on entropy and disorder. Planck was trying everything, basically bending his own rules, trying to find a mathematical formula that fit the experimental data, even if he didn't fully understand why it worked.
And that led him to the breakthrough in 1800, the famous equation.
That's it. 1, energy equals Planck's constant, h times the frequency. No. Simple looking, but revolutionary.
Okay, unpack that. Why was Duigno such a bombshell?
Because it meant energy isn't smooth. It's not continuous, like water flowing. Planck was forced to propose that energy can only exist in discrete chunks. Fixed amounts. He called them quanta.
So it's like energy comes in packets, not a stream, like climbing stairs instead of rolling up a ramp.
Perfect analogy. You can be on step 1 or step 2, but never halfway between steps. Energy exists only in these specific quantized levels.
And the size of the step is set by this h, Planck's constant.
Which
is tiny, right?
Unbelievably tiny. It's $6.63 times 1034 joule seconds. I mean, that number is so small, it's hard to even grasp.
Which explains why nobody notices graininess before. On our scale, the steps are just too small to perceive.
Exactly. For everyday objects, the energy steps are so minuscule they blend together, looking continuous. Like that staircase looks like a ramp from far away. But down at the level of atoms, single photons, these tiny steps are everything.
So Planck's desperate fix establishes two huge things right away. One, quantum effects are for the very small scale. And two, it's inherently statistical, probabilistic.
Absolutely. Classical physics says, hit a pool ball the exact same way 1,000 times, it does the exact same thing 1,000 times. Deterministic.
Right, cause and effect.
But quantum physics says no. You can only know the probability of an outcome. You shoot an electron, you know the odds of where it might land, but you can't know for sure until you measure it. It's fundamentally based on chance.
Which, ironically, Planck himself hated. He came up with it, but didn't really believe it was real.
Not really, no. He thought it was just a mathematical trick, a temporary scaffold he could remove later once he figured out how to make it fit back into the old, continuous, deterministic physics he loved. That's why they called him the reluctant revolutionary.
So what pushed his idea from mathematical trick to accepted physics?
That was Einstein. 5 years later, 1905, his miracle year. Einstein took Planck's quanta idea deadly seriously. He used it to explain something else entirely, the photoelectric effect.
Where light hitting metal kicks out electrons.
Exactly. Einstein proposed that light itself travels in these discrete packets, photons carrying energy defined by E to do. That application, explaining a different physical phenomenon, that's what really convinced people Planck was on to something physically real.
Okay, so Planck quantizes energy. Now let's bring in Niels Bohr. He takes this quantum idea and applies it to the atom itself.
Right. So we need a quick picture of the atom at that time. We'd gone from the Greeks' atomos, uncuttable thing, through Dalton's chemical atoms, Mendeleev's table.
Then J.J. Thomson finds the electron, this tiny negative particle inside.
And then Ernest Rutherford does his gold foil experiment and finds the atom is mostly empty space with a tiny, dense, positive nucleus at the center.
Which leads to Rutherford's model. Tiny negative electrons orbiting a positive nucleus. The planetary model looks neat, but it had a fatal flaw, didn't it?
A catastrophic one, according to classical physics. Remember, classical electromagnetism, Maxwell's equation, says that any accelerating charged particle has to radiate energy.
And an electron orbiting in a circle is accelerating, right? It's constantly changing direction.
Precisely. So it should be constantly losing energy by radiating light.
And if it's losing energy?
It should spiral inwards, faster and faster, crashing into the nucleus. Calculations showed this should happen in about 0.00000000000 seconds, 100 millionth of a second.
Wait, so every single atom should collapse almost instantly?
Yeah.
But they don't. Matter is stable. Tables, chairs, us. We exist.
Exactly. It was complete breakdown. Rutherford's elegant model, combined with the trusted laws of electromagnetism, predicted that matter shouldn't exist. A total paradox, an existential crisis for physics applied to matter.
Okay, so the stage is set for Bohr, 1913. How does he use Planck's quantum idea to save the atom?
Bohr basically said, okay, classical rules clearly don't apply inside the atom. He made some bold leaps, his 3 famous postulates.
What was the biggest leap, the core idea?
Postulate number 1, stationary orbits. This was the big one. Bohr just declared that electrons can exist in certain specific orbits, certain energy levels, without radiating energy. Period.
He was an exception to Maxwell's laws for those specific orbits.
He did. He said, in these allowed stationary states, the electron is somehow exempt from the rule that says it must radiate. It was a radical, almost arbitrary-seeming move, but it solved the stability problem instantly. If they don't radiate, they don't spiral in.
Okay, so they can exist in these special orbits. How do they move between them? That's postulate 2.
Right. Transitions. An electron can jump from one allowed orbit, energy level, to another. If it jumps to a higher energy orbit, it has to absorb a photon with exactly the right amount of energy, the difference between the 2 levels.
E photon, E2, E1.
Exactly. And if it falls from a higher orbit to a lower one, it emits a photon with that precise energy difference. This explained where atomic light spectra came from.
The specific colors emitted by elements when heated, their fingerprints.
Precisely those fingerprints. And postulate 3 gave the math for which orbits were allowed.
The quantization rule for the orbits themselves.
Yes. Bohr proposed that only those orbits where the electron's angular momentum was a whole number multiple of 2 Rddt, Planck's constant divided by 2 pi, could exist. This provided the mathematical structure, the reason for the steps in the atomic staircase.
And this model, despite its, well, weirdness, it worked incredibly well, didn't it? Especially for hydrogen.
Amazingly well. It perfectly predicted the wavelengths of light emitted by hydrogen, matching the known spectral lines, like the Balmer series, which had been a mystery for decades.
Even J.J. Thomson, who discovered the electron, was impressed.
Yeah, Thomson called Bohr's explanation ingenious and suggestive, but also admitted the only justification at the time was the very weighty one of success. It just worked, even if nobody quite understood the why behind Bohr's rules yet.
So, zooming out again. Planck and Bohr together, they didn't just tweak physics. They forced this massive philosophical shift. You had to accept things that just didn't make sense in the everyday world.
Absolutely. You had to, as someone put it, leave what you think you understand by the wayside. Especially the idea that reality at its base is statistical, not deterministic.
Which brings us back to Einstein's discomfort. He used quantum ideas brilliantly for the photoelectric effect, won his Nobel Prize for it.
But he could never accept the probabilistic core of it. He spent years arguing against it, famously saying, "I, at any rate, am convinced that he, God, does not throw dice."
That philosophical resistance from giants like Einstein must have slowed things down.
It certainly contributed. The implications were just so profound, so alien to the classical worldview, that acceptance wasn't immediate, even with the experimental successes piling up.
Now, Bohr's model itself isn't the final picture of the atom, is it? It got updated later.
That's right. Later developments, like Schrödinger's equation, gave us the fully quantum mechanical atom. No more neat orbits, but rather probability clouds regions where the electron is likely to be found. It fully embraced the statistical nature.
But Bohr's model is still taught, still used.
Oh, yeah. It's often the first model people learn because it's visual. It captures the key ideas of quantized energy levels and transitions really clearly. For a lot of basic chemistry and physics, it's still good enough, even if not strictly correct.
And the fully fledged quantum mechanics that grew out of this. It's not just theory. It's the foundation for so much modern tech.
Everything. Lasers, transistors, computers, MRI machines, flash memory, all rely on understanding and manipulating quantum effects.
And this brings us right up to today, because we're now building things so small that these quantum effects aren't just useful, they're becoming problematic.
Exactly. Think about Moore's law, the idea that computer chips get exponentially smaller and faster. We're now making transistors that are just like 3 nanometers across, maybe even 2.
It's incredibly small. Atoms are like, what, 1/10 of a nanometer?
Right. So we're talking features made of just a few dozen atoms. And below about 7 nanometers, weird quantum stuff really starts to dominate. Specifically, something called quantum tunneling.
Okay, quantum tunneling. Sounds like science fiction. What is it?
It's maybe the weirdest consequence of the probabilistic nature of quantum mechanics. Imagine an electron trapped behind a barrier, like inside a transistor component. Classically, if it doesn't have enough energy to go over the barrier, it stays put.
Makes sense. You can't walk through a wall.
But quantum mechanics says there's a non-zero probability that the electron can just appear on the other side of the barrier, even without enough energy to overcome it. It tunnels through.
It just pops through the wall by chance.
Basically, yes. Because its position isn't definite, it's probability wave. And that wave extends slightly into the barrier and even beyond it. So there's a small but real chance of finding it on the far side.
And this is a real problem for making tiny computer chips. Electrons leaking out where they shouldn't.
A huge problem. It causes errors, uses power. Engineers have to design around quantum tunneling now. We're building tech that is limited by the fundamental probabilistic rules Planck first stumbled upon.
Wow. It really highlights how deep this goes. Even the experts find it baffling, right? Wasn't it Feynman who said it?
Richard Feynman, yeah. Nobel laureate, brilliant physicist. He famously said, "I think I can safely say that nobody understands quantum mechanics." And he worked with it every day.
So to wrap up, Planck and Bohr, with these papers, they didn't just solve some physics problems. They laid down a completely new foundation for science. It's up there with Galileo or Newton, isn't it?
Absolutely. A fundamental shift in our understanding of reality. They showed us that certainty, continuity, determinism, these are illusions of the macroscopic world. Underneath, it's all quantized, probabilistic, and frankly, weird.
And here's maybe a final thought for you listening to this. Even quantum mechanics, our most successful, most accurately tested theory ever.
Might not be the final word. That's the nature of science, right? Just as classical physics gave way to quantum, maybe there's something deeper still waiting to be discovered. We have this incredibly powerful tool, but we acknowledge it might just be a better approximation, not the ultimate truth.
So the very stability of the world you see, the solidity of the device you're listening on, it all runs on principles that are fundamentally uncertain, statistical, and maybe, just maybe, incomplete. Something to think about.
Keep digging.